And you're welcome to get started. We're on YouTube now.
Okay. All right. Welcome, everyone, to the session on functional encryption and attribute-based encryption. Our first speaker is Miguel Ambrona, who's telling us about generic negation of pair encodings.
Yeah, thank you for the introduction. So I assume it's been seen properly. Yeah, so in this work, we propose a generic negation of pair encodings. And pair encodings are a primitive that is used to build attribute-based encryption. So, in attribute-based encryption, everybody can encrypt. And when they produce a ciphertext out of their message, they are thinking of certain policy. Yeah. And the system is such that only those users who own a secret key with attributes satisfying the policy will be able to decrypt the ciphertext. And this secret key has been requested and has been produced by a master authority. So, okay, more generally, when you encrypt, when you produce a ciphertext, you associate the value X to the ciphertext. Every secret key has a value Y associated, and decryption works only if a predicate between X and Y holds. And there are many techniques, there are many works for building full secure attribute-based encryption systems. And the one I'm interested in is this technique called pair encodings, which was introduced by Atrapadung in 2014. And it's a very nice idea. You can focus on building a pair encoding for a certain predicate. And then there is a compiler that gives you a full secure attribute-based encryption system out of that encoding. And this is very nice because analyzing the encoding is much simpler than analyzing the attribute-based encryption scheme. In this talk, we focus on pair encoding schemes. And a very natural question is whether you can transform or combine pair encodings. These are, for example, some combinations that have been considered in the past. So given a pair encoding scheme for a predicate P, you can build a pair encoding scheme for its dual predicate. The dual predicate just swaps the roles of X and Y. Or if you have two pair encodings for two different predicates, you can make one for the conjunction. This was done by Atrapadung and Yamada 5 or 6 years ago. And you can also do disjunction. Disjunction is very easy. But how about negation? So negation seems a lot harder, and this was not done before. I have to say that this was done in a different framework, very nice, also introduced by Hotek, by the way, predicate encodings. So in this framework, we knew how to generically negate a predicate encoding. But in the framework of pair encodings, which are believed to be, well, they actually are more general, we didn't know how to generically negate them. So this is what we do in this work. So our main contribution is a generic transformation that takes any pair encoding scheme for a predicate P and produces a new pair encoding for the negated predicate. So along the way, we propose an algebraic characterization of pair encodings that I believe can be of independent interest. And we also explore other consequences of these results. And this is what I want to talk a little bit about in the rest of this presentation. So first of all, we found new encoding. So there was this pair encoding scheme by Atrapadung for the doubly spatial encryption predicate, which is this one. And it was unknown how to build a pair encoding scheme for the negated predicate. So negated doubly spatial encryption. And we can use our transformation. We have it for free, and in fact, we can have the negation of any pair encoding scheme without having to design it. So I want to say that I'm very grateful to Atrapadung because he's the one who pointed out that this problem was open, and it made my paper much stronger. So thank you so much for that. Okay, other things I want to mention. The expressivity of pair encodings. I think our new result brings new non-trivial information about the expressivity that can be achieved with pair encoding schemes. So for example, what I mean is that the set of predicates that we can handle is closed under negation. So one of the consequences of this observation is that maybe building a pair encoding scheme for context-free languages is harder than we think. Because, context-free languages are not closed under complementation. So if we could build a pairing coding scheme for a context-free language, we would have also a pairing coding scheme for some class that is strictly more powerful than context-free languages. So this suggests that maybe it's already hard to achieve context-free languages, or maybe it's impossible with pairing codings, given this observation. And other consequences that we explore in the paper are potential performance improvements. So our transformation, I didn't show how the transformation looks like, but it gives a very specific structure on the produced encoding, and it actually shows that any encoding can be expressed in this form. And we explore several ideas that exploit this structure to produce a faster implementation. So for example, you can pre-compute some part that does not depend on the predicate and only perform an online computation on the part that actually depends on the predicate. So it'll be a very interesting direction for future work to implement and really test whether these ideas lead to something. So yeah, that's everything I wanted to say. Thank you so much.
Thanks a lot, Miguel. We have time for like a quick question, maybe? Okay, so we have a question from on the chat. It looks a bit long, but maybe we can put it to the end of the session. Or maybe I can try to read. So, right. So if you apply your generic negation transformation to the, say, the unbounded KP-ABE formal constant programs for in the Atrapadon's Eurocrypt 2019 paper, do you get the same scheme as the one for non-monotone, or is your generic negation different?
Yeah, I guess it's probably different, but I'm not sure. I'm not very familiar with the framework of dynamic composition, but my guess is that it's very different.
Okay, maybe we can try to take this to the.
I have no idea. So I can look at that and give an answer in a few days to whoever asked.
Okay, all right. Let's thank Miguel, and let's proceed to the next talk. Do we have Shenyuan Feng around?
Yeah.
Yep. Okay, great. So our next talk is Master Key KDM Secure ABE via predicate encoding by Shenyuan Feng, Chunxing Gong, and Jie Chen. And Shenyuan will give the talk.
Okay, thank you. Oh, let me share my screen. Okay. So, thank you. Hello, everyone. I would like to share our work about framework of attribute-based encryption with master key KDM security. It's a joint work with Junxing Gong and Jie Chen. And in this work, we studied the master key dependent message security for the find function. That is, the encrypted message is a find function of a master key, and the adversary cannot distinguish the key dependent message and random message, even obtaining multiple mismatched ciphertext and secret keys. And we use the notion of predicate encoding, which provides a simple description of the underlying predicate P, like IBE, HIBE, ABE for ABP. So by concurrent encodings, we propose the first MKDM secure HIB schema and the first MKDM secure ABE schema for ABP under standard pairing-based assumption. Thanks to the expressiveness, we combine the classical CHK CPA to CCA transformation and obtain CCA security. And in the context of IBE, we can also derive an IBE schema from our framework. It enjoys constant size master public key and achieve MKDM CCA security. As a start point, we first revisit GGH20 schema, and next I will show the main idea behind our proof. So both our schema and GGH schema use three bases simulating three subgroups in the composite order groups. And here is the GGH20 schema. They show a clever combination of KTM secure PKE and tie secure IBE. By the type reduction of IBE, that's a variant of dual system technical. They can extract the entropy. By this entropy, they can carry out the KTM argument as in BHH08. But however, their proof relies on the structures of secret key and the ciphertext, so it's not general for our schema. In this work, we employ another variant of the dual system technical. It's slightly different to the standard dual system technical. We first change secret keys and then change the ciphertext one by one with another next argument. And in final, we change all ciphertext and secret keys. At this point, one can control the leakage of master secret key and in the message using the entropy, and then carry out the KTM argument for PKE. Okay, let's all thank you.
Thank you very much. That was quick. Do we have any questions for the speaker? Let me just quickly check Tulip.
Maybe I can ask a quick question. So are there specific applications where you need KTM security of those schemes?
Sorry, my network has some problem. Can you repeat your question?
So do you know any specific applications where this property is needed to gain proof security?
Oh, I'm not sure about this. Sorry.
No worries. Yeah, I mean, it's good to have, but I was wondering whether it's really kind of arises out of specific applications.
Okay.
Okay, any other questions? Okay, then maybe we take further questions at the end of the session. So I'm going to hand off to my fellow session chair to introduce the next speaker. Thanks, Xuan.
Okay, so hello everyone. So the total of this session will be multi-client functional encryption for separable functions. And there are three authors to that paper, Michele Campi, Luisa Siniscalchi, and Hendrik Wallner. And the talk will be given by Hendrik. So Hendrik, so the screen is yours.
Thanks for the introduction. So yeah, this talks about multi-client functional encryption for separable functions, joined with Michele Campi and Luisa Siniscalchi. And in this work, we consider the setting where we have different parties that provide encrypted documents. So we have Alice and Bob, and both of them provide some encrypted documents. And now we want to allow Dave and Aaron to do some analysis over these documents. So in this setting, we want Dave wants to learn how many times the word PKC occurs in both of these documents. And Aaron wants to learn how many times the word crypto appears in both of these documents. And while allowing for their evaluation, we still want to preserve the privacy of the encryption. So they should really only learn their desired word count and nothing beyond that. And the cryptographic primitive that we can use to achieve this is multi-client function encryption for separable functions. So a separable function is an n-input function that can also be evaluated if you evaluate n single input functions and applied on the different inputs and sum up the results. And in a multi-client scheme, we have a setup algorithm that outputs several encryption keys and the master secret key. The encryption keys can then be used by the different clients to encrypt their messages together with an encryption label. And the master secret key is used in a key generation procedure to generate functional keys. And if Bob is in possession of such a functional key, he can compute the function evaluation of his key applied on the plain text encrypted by Alice and Carol. And this decryption only succeeds if the ciphertext he uses are generated with respect to the same encryption label. Yeah, in this work, we show how to realize multi-client function encryption for separable function from secret key single input schemes. And this is basically a similar setting where the setup algorithm only outputs a single key that is then used for the key generation and the encryption. Yeah, there also exists a decentralized version of this notion where there's basically no setup algorithm that is executed by a single party, but Alice and Carol do this together interactively. And then for the generation of functional keys, they can both generate different functional key shares, which can then be combined to obtain the full functional key. Yeah, in terms of transformation from single input functional encryption to multi-client functional encryption, there have already been some work. The first work is by Brakersky et al., where they show how to turn a secret key single input scheme into a multi-input scheme. The notion of a multi-input is very similar to the multi-client notion. They have a different security definition and they don't incorporate encryption labels. And they do this for a general class of functions. Then there's some other works on a more specific function class, the inner products. And there's been a work by Abdallah et al. Where they show how to lift a secret key single input scheme into the multi-client setting without labels. And in another follow-up work, it has also been shown how this scheme can be decentralized. Then in another follow-up work, the previous construction has been extended to labels. So it also incorporates labels. And they have to switch from a secret key single input scheme to a public key scheme. And yeah, as already mentioned, we focus on the transformation from secret key single input to multi-client for separable functions. And we additionally also introduce a new notion that allows for distributed execution of the decryption procedure, which we will see later. So yeah, how does our construction work? So our construction basically runs n different instances of a single input function encryption scheme. And when a functional key for a separable function is requested, functional keys for all the individual functions are generated, and these functions then output the evaluation together with a secret share of 0. So this secret share is used to hide the individual function evaluation and to prevent the combination from individual keys with other individual keys from a different separable function. And we need a similar property for incorporating labels in the ciphertext, such that we cannot combine ciphertext encrypted under different labels. And here the issue is that this secret shares cannot be generated by a single party, but the clients have to do this non-interactively on the fly. And we can accomplish this using a specific PRF technique. So then in the end, the individual functional keys will output the individual function evaluation, plus the encoded share inside the key, plus the share incorporated in the ciphertext. And if all these values are summed up together, the final output can be obtained. Yeah, this scheme is not yet decentralized, since we say we generate these R values by a single party does this, but we can simply use again this PRF technique to also do this in a distributed way. So yeah, let me say something about the notion of outsourceability. So an outsourceable multi-client function encryption scheme is similar to a multi-client scheme, with the difference that the key generation procedure outputs different functional key shares, which can then be used in a partial decryption procedure to generate decryption shares, which can then be combined to obtain the final output. And security here ensures that these shares, these decryption shares, do not leak anything about the final function output. And this notion is particularly useful if this partial decryption procedure is quite heavy, such that it can be outsourced to someone with more computational power. And our scheme directly realizes this notion by just defining the partial decryption procedure as the decryption procedure of all the single input schemes. And then the combination is simply the sum of all these values. Thank you for listening.
Okay, so thank you, Hendrik. So other question for the speaker?
Maybe a quick question. Can you go back one slide for where you do the partial decryption? So I think there's a separate partial decryption for every encryptor. I'm curious what happens if you kind of apply the decryption immediately after the encryption, whether this gives rise to some encryption scheme that already exists, like that allows you, for instance, to aggregate the results. But so I wonder whether there's some relation to existing schemes when you just combine your encryption and decryption for these individual parties. Have you thought about that, or does it not make any sense at all?
Well, the thing is that then you're already like kind of committed to the function, right?
Yeah.
I mean, the advantage here is that you can,
yes, I see that, but I suspect that there are some constructions in the literature that kind of commit to the assumption. For instance, are computing just the sum of the inputs, and so that you are a special case of those constructions. And I was wondering whether, for instance, there's some kind of aggregation scheme, private aggregation schemes, which you would now be a special case of.
Yeah, probably. I mean, if you know the function previously, I don't think why this should not work.
Okay, any more questions? No? Okay, so thank you, Hendrik. So let's move to the last talk of this session already. So the title of the paper is still composable hardware-based stateful and randomized function encryption. There are 4 authors, so Pramod Batotia, Markov Kolweis, Lorenzo Martinico, and Yanis Tselikunis. So I'm sorry if I did not pronounce your names correctly. And the talk will be given by Lorenzo.
Right, thanks, Mark. So let me start with a motivating example. Let's take the problem of classifying encrypted messages as fake news. Of course, we could try to download a heavy data set of fake news articles to our mobile client, but that's untenable. So the best approach seems to send the message unencrypted to the cloud, let the cloud run its classification algorithm, update the data set with the new message, and then return the classification to the client. Of course, the disadvantage of this is that we reveal the client's correspondence. So what we can do is run a functional encryption scheme such that we can run this analysis function on the encrypted ciphertext and still return a classification. Our work expands the class of functional encryption functions that we can compute to include stateful and randomized functionalities. And we instantiate a protocol that can implement them securely, proven under the UC model using trusted execution environment in Pass et al.'s formalization. And then finally, we relax the model from Pass et al., PST, to capture additional adversaries. So our protocol is called Steal, and like the title says, is composable, hardware-based, and implements stateful and randomized functional encryption. So when we talk about randomized functionalities, we mean that any attempts at decrypting can use a fresh random string. This is different from previous notions of randomness in functional encryption, where we'd have randomness come from a new functional key. And then when we say stateful, we mean that each of our decryptors can hold some kind of state for each of the functions they want to compute, such that any decryption can update this private state. In practice, the class of functions that we can implement, that we can compute in a function encryption scheme, takes in as additional input a state string and a random string, and return an additional state string. Our Steal protocol, as I mentioned, is based on trusted execution environments, which are extensions on CPU architectures that guarantee additional properties like confidentiality and integrity. In particular, our work is based off Iron by Fish et al., which already implements public key functional encryption using Intel SGX. Within our protocol, we have the decryptor and the key management authority as SGX-equipped machines. The encryption phase is simply a plain public key encryption conjoined with a plain text proof of knowledge. And the key material for public key encryption is kept within the 2 enclaves confidentially, and it's only exchanged if the 2 enclaves can convince each other that they're running the genuine Steal code. The functional keys are simply signatures over a representation of the function, which the decryption enclave will verify to be authentic before authorizing decryption. Our proof is in the UC with global subroutine setting, where we can add a global functionality to any UC protocol. And in particular, we formalize. In particular, we use the global attestation functionality from Pass et al. To add our hardware-based functionality. Some details from the proof. One particular challenge that we have is that we need to synchronize the state of the ideal functionality without a simulator. So as we mentioned, whenever we run a decryption, the state, the inner state to the decryptor gets updated. So whenever the environment picks a challenge ciphertext, because it encrypts it using the public key encryption, the DL functionality has no notion of this encryption phase. So we need to extract somehow the message. And this is why we add a plaintext proof of knowledge, which the simulator can use Disruptor to obtain back the original message X and pass it on to the DL functionality, just like it would have happened in the real world where the enclave would decrypt the ciphertext using its key. Finally, we model an additional relaxation over the PSD functionality to allow two different kinds of attacks. So in the honest setting, any update to the state would proceed in such a linear fashion, like in the figure. However, we model an additional adversary that can conduct a rollback attack, where after some states, it can rewind it to a previous state, as well as an adversary who can conduct a forking attack, where you can hold different branches of the enclave at the same time. We showed that Steal is vulnerable to both this kind of attacks and discussed some potential mitigations from the literature. Thank you. These are the main takeaways of our paper, and I'll take questions now.
Thank you, Lorenzo. So other question or comments? Maybe a quick one then on my side. So if you find a new extension, so you may call it silver or gold, so depending on the results.
Yes, that's the next paper.
No questions? So maybe then we can recap for all the talks. And so if you have any question for any of the previous talks, so feel free to ask. You can also check on Zulip. So I don't know if there are questions there.
Yeah, Miguel, maybe a question for you regarding the generic negation, sort of follow up to the previous questions. For most of the predicates, the encoding that you get from generic negation, do they match the previous encoding for the negated predicate?
Hi, sorry, I missed the first half of the question because I was refreshing my browser.
Oh, actually, no, that's fine. Sort of like, is it the case that for most predicates, if I apply your generic negation, the encoding I get is the same as the existing encoding for the negation of the predicate?
Okay, so I don't think so, but maybe after simplification, it is the same. So I remember that for the predicate encoding negation that I also developed 4 years ago, that was actually the case for many encodings. So if you first negate and then simplify, you were getting the actually negated encoding that some human had developed independently.
I see.
And it was, and by some human, I mean you, basically, because you developed most of the predicate encodings. Yeah, so something interesting that I want to point out is that sometimes after negating, you were getting something even simpler. So for example, that was the case of monotone spam programs. So you were getting something that was even smaller than the original encoding, but you have to simplify. Negation is generally bigger. It'll grow, but maybe you can simplify. You can, find some linear combinations that simplify, and you get something smaller than the original. And I have not observed this phenomenon in the new one, but in parent encodings, but maybe it happens. That's an interesting question, whether it will happen or not.
I see, but can you apply the simplifications even before applying the negation, or the simplification technology is inherent to having applied the negation transformation?
Right, so first of all, I don't really know how to systematically simplify a parent encoding. So there were some ideas in the predicate encoding framework. In parent encoding, I have not really a good idea how to do it. But I don't think those simplifications were not working on the original encoding.
I see.
So it's when you introduce the redundancy after negating, it turns out that you can simplify even farther, but those simplifications were not giving you anything on the original. And this is some weird phenomenon that I could not find an explanation for even after a few years. Maybe someone can give new insights.
So that sounds like a great open question.
Yeah.
Do you have any other questions for either Miguel or the other speakers? Maybe one of your co-authors can try to answer Marco's question from earlier about motivations for KDM.
You're calling me?
Yeah, maybe can you answer Marco's question earlier about motivations for KDM?
Yeah, true. So for the KDM, so the main difference or what they enhance the security is that you can encrypt something related to key. So the trivial case is that you can encrypt a key. So for the standard CPA or CCA, you cannot do this. So for this point, we can have several applications or some scenarios we need it from a theoretical part or maybe real world application. So for the theoretical part, so maybe you all know that for the homomorphic encryption, we need bootstrapping. You need to encrypt some key for the next round. For the application, we saw a scenario that described in previous papers. That's if you have an IB system, something like this. So you want to do some revocation. You have some time period. Then you can encrypt the secret key for the next round, for the next time slot, using the encryption system for the current time slot. So in this case, you need to encrypt the key using the same encryption system. So this is what we know for this for the applications. For our work, actually, we follow the line that extend the expressiveness from PKE to IBE to ABE. That is somewhat a natural desirable things we want to have. But for this, we also give an application. So for the extension from PKE to IBE, we can do something like PKE with CCA security and also KDM security, because we need IBE to do this. I mean, we need a KDM secure IBE to work with the transformation, so the classical one. So for our work, we use the same paradigm to show that an AB scheme with KDM is also useful, because we can get CCA secure and a KDM for IB scheme. So that's what we all know for the application. And also it's really an interesting question to find more application. I mean, in the theory part, I mean, how to use AB with such kind of expressiveness, because we can do KDM AB for from the pretty encoding. That means we can do very expressive AB. So yeah, I think it's an interesting direction to find more application. Yeah, I hope this answered the questions.
Yeah, no, very, very detailed answer. Thanks a lot. I have another question maybe on applications. So I was wondering whether the functional encryption community sees value in, for instance, using hardware to implement things that at the moment are too inefficient, but that can later on could be used with cryptographic solutions for general functions. So whether this is a way of exploring the potential of using functional encryption in applications. I don't know, maybe Henrik wants to say something on that. I don't know. But I don't want to pick anyone out, but just curious what the other speakers of the talk thought about that.
For me, I don't know so much about the hardware implementation, but I made some work for SGX or something like this, but I didn't check the paper, I guess. So if anybody know more, I would like to hear about it. Yes, it is true that for this it's a good point.
Yeah, so we had the same for IBE. So the very first implementation of IBE basically was using a smart card. So that was a long time ago by the Smet and Kiss Carter. So I don't remember when, but and then came those pairings, and then all the stuff you know. I mean, that's natural to look at the solution. I mean, there is nothing else available.
Do you know who did this smart card implementation of functional encryption?
Yes, it was Desmet and Kiskater. I forgot the year, so I don't want to say something wrong, but
yeah,
it's good
that Ivo Desmet is not here. He would have shouted at us.
Yes.
Yeah, in the talk. Okay, that's very good.
Yeah, we are missing that too. Okay, very good.
Late 80s.
Late 80s. Thank you, Moti.
Yeah, but there's also been research work looking into using secure hardware to accelerate fully homomorphic encryption. So I think it's a matter of time that we will also start looking into using hardware to accelerate our functional encryption.
Yeah, but there's a difference between using hardware and tamper-proof hardware, which the user itself doesn't see the inner working. Like the public key that has actually based on a secret key there that does a symmetric encryption and claim to be public key. It was done by Desmet Kiskater. It was part of an IBM old architecture in the 80s too. It's all tricks. They always come back in a new format when there are more new primitives.
Yeah, I think there's work also on using minimal hardware tokens to implement functional encryption. So there's also more theoretical work in that direction.
Yeah. All we say is that there are now new dimensions to the old work. It's not exactly the old work. New primitives.
So actually building on that, coming back to Lorenzo and the last work, when you use your hardware and your enclaves, is there a sense of how simple can you make the functionality you require from the trusted hardware components?
So sorry, can you say it again? By simple, do you mean like?
So you require some trusted hardware, right?
Yes.
So and then you need a trusted hardware to do some computation for you. How simple can this computation be?
I think that's a great question. I think it's somewhat a trade-off between efficiency and security, because obviously we know trusted hardware has some problems like side channel attacks. So right now in our construction, we basically rely exclusively on the trusted hardware to do the entire computation, which has some trade-offs. But so we've been thinking about trying to add in more crypto outside of the enclave itself to strengthen it. But obviously that would mean a decrease, because just running the code in the enclave has basically no performance impact, but any further crypto we have to do would affect that. I hope that answered the questions.
Yeah. So we have the test of times award ceremony coming up, so we should try to end on time. We have 1 more minute. Any other final comments or remarks or questions for the speakers? If not, maybe we can take further questions to Tulip, and let's thank all the speakers again for the session. All right, thank you. Oh wait, we still have 1 minute, so questions after the applause. Maybe we can finish a little bit early. Thank you, everyone.